Today we're going to talk about graphing square root functions. Square root function is a function that contains a square root with the independent variable in the radicand. The parent function for the family of square roots is the f of x equals the square root of x. And we've seen that from a lot of the different parent functions are the ones we compare things to. The domain of function f of x is greater than 0. And the range of f is also y is greater than or equal to 0. And you can see that right over there from the graph. So we can kind of see here that we would have only things that are going up in the positive on the parent function, and also on the x's we don't have anything continuing on this direction. So it's always x's are greater than 0 or equal to 0, and the y's are also greater than or equal to 0 for the parent function. It makes sense if you think about it. My x values, we've always said so far this year that they've always been all real numbers. But for this one, I can't have a square root of a negative number. So those are not possible on the graph. So as I said, the value of the radicand in the square root function cannot be negative. So the domain of the square root function includes x values for which the radicand has to be equal to or greater than 0. In this case, it's easy to see. We want to look at some of these other examples. So for this first example, describe the domain of this coming square root function, which is f of x. So this time we see 3 times radical x minus 5. So we want to know what is the domain. So the domain, if I look into this right here, the radicand has to be greater than or equal to 0. So basically, I set this to look like that. Now I can just do a quick, simple solve my inequalities that we did earlier this year. And so my x values, or my domain, for this function will be any x value that is 5 or greater. And if you think about it, that kind of makes some sense, because if this was a 5, this becomes 0. I can do the square root of 0, which would be 0, and then I could multiply it by 3 to get my y value. If it was greater than 5, for example, 6 minus 5 is a positive number. I can take the square root of a positive number and multiply it by 3 to get my x value. So the radicand in a square root function has to be a positive number or 0. So now we want to graph one of these. So we're going to see some different things that we can do to try to see the shortcuts. A lot of the shortcuts that we've used throughout all these different functions, starting with linears and all the nonlinears, are still similar, but we want to think about a table. Okay, so at first, if I was to make my table, I want to be careful here. So my table, I want to only put in values that are going to be true values. So again, we just said a moment ago that the radicand, the thing under the radical sign, has to be 0 or positive. So I'm not going to pick x values, for example, here, that would be -2s or -1s, because in this function, this has to be 0 or higher, because there's nothing else underneath the radical sign with it. So here's some that I would pick. So I'm going to first pick x's are 0. Now, I want to be smart here. I want to think about things that are perfect squares, because it'll make things easy for me. I want my radicands to be perfect squares, so I don't need to worry about calculators and rounding. So let's just make a quick list down here. So my perfect squares, as a reminder: 0, 1, 4, 9, 16, 25, and it keeps going. So just as a reminder, I would like my radicand, not just the x's, but in this case just the x's, but as I look through all of these, my radicands I want to be square and perfect squares. So for this one, I would pick numbers like 0, 1, 4, 9, and well, let's just go to 16. We'll get 5 points out of this. Now I'm going to use my order of operations. Okay, so this says take the square root of x, add 3 to it, That gives me 0 plus 3, which is 3. When 1 goes in, I take the square root of 1, which is 1, add 3 to it, and I get 4. If I put in 4, I take the square root and get a 2, add 3 to get a 5. If I put in 9, take the square root, that gives me a 3 plus 3 is a 6. And then if I put in 16, take the square root, which is 4, and I get 7. So there is a table from this function that I can now put into play to set it up to show the graph. So as all of these values are positives, I'm only going to draw quadrant 1, but I'm going to show those little arrows because they're showing all 4 quadrants, but we're only going to be seeing these values in quadrant 1. So now as I just plot these points, actually I think I'm going to do my y's will go by 1s. But my x's, we need to go by 2s, I think, to fit. And it just makes it. Okay, so 0, 3 would be sitting right here. 1, 4, somewhere in there. 4, 5, 9, 6, and 16, 7. Now, it's not linear. You can see that it's not linear. We also want to make sure that we are drawing a nice smooth curve the best we can through these points, and notice that they are going to continue to rise. So I want my arrow showing that they're going to continue to rise. I don't want it to look like it's dipping back down. It's not a parabola. I also want you to notice that on the beginning, I don't have an arrow here because it would not continue onto this side, because this would now be giving me radicands that are negatives, which aren't possible. So this is a ray looking. And that would be the graph. Okay, and then the second part of this says is to describe the domain of the function. Well, if you look at the domain of the, describe the range of the function. So remember, range are the y values that we see. So our range, our y's are greater than or equal to 3. That answers that second part of the question. A radical function is a function that contains a radical expression with the independent variable in the radicand. So that sounds pretty fancy, but basically a square root function is a type of radical function. So it doesn't have to be square roots, and we're going to see some of that in our next section. We can have cube roots, we can have fourth roots that are functions. So a radical function is any kind of a function that has a radical expression with the independent variable inside of the radicand. Okay, we can transform graphs of radical functions the same way we kind of saw through a lot of the things that we've done this year. So remember, we talked about our horizontal translations. So like our absolute values, and when we did our quadratics, the numbers on the inside are kind of doing the opposite of what they think for our horizontal translations. If it's a -2, we're going to go to the right 2. If it's a +3, we're going to go to the left 3. Then we talked about the vertical translations, which shifts them up or down. It's the plus or minus what it looks like. So +7 goes up 7 units. -1 would go down. And notice these are outside of the radicand. They're not in the radical. The reflections, we talked about the numbers in front, the a values, or in this case now the coefficient in front of the radical. If it's a positive, it's going to be up in the y-axis, and it's going to reflect down into the as a reflection over the x-axis if it's a negative. So we'll see some of those in a minute. Then we have the horizontal stretch or shrink. Basically, we didn't talk about these as much, but the horizontal stretch kind of, when we see numbers on the inside, it is kind of shrinking by a factor of the 1/3, and the stretch factor of a 2, if it's a 1/2, it would that would be your horizontal stretch. The vertical stretch, when we have that number out in front, like this, for example, this number that was greater than 1 for this 4, it kind of stretches it up steeper, which makes it close a little bit, so we'll see it rise quicker. This one would be rising lower, so it's more of a shrink vertically. Don't worry about those so much, because once we start making tables, it kind of takes care of a lot of those things. But those are some of the things we want to be looking at when we are asked to describe. Okay, so here's another graph. So this time we want to draw a graph of the function g of x, negative square root of x minus 2. So first we want to think about what's our table going to look like. You know, we have this table over here that we might say, well, we want to plug in some x's and some y's, and we want to figure out what some points are. But how do we know which points to be looking at? Well, we talked in the beginning here of taking our radicand, which is the x minus 2, and solving it greater than or equal to 0. So now it's not just an x on the inside. Now I have to be using values of x that are greater than or equal to 2 for my domain. So if somebody asks me what's the domain of this function, it's going to be x is greater than or equal to 2. But I'm going to use that in my table. So, for example, 2 will be one of the x's that I'm going to use. And you might say, well, that's not a perfect square. However, if I plug 2 into here, 2 minus 2 becomes 0. So when I do 0, then that's going to give me the perfect square I need. So it's the overall expression that gives me the perfect square, not the x that goes in. So for example, negative 2 minus 2, that's the negative square root of 0, which is perfect. So the y would become a 0. So then I want to think, well, what's the next perfect square? Well, the next perfect square here we might want is 1. So how do I get a 1 from x minus 2? Well, that would give me a 3. So the negative 3 minus 2 equals the negative square root of 1. Perfect. I'm just going to draw this little line to separate this out. So that would tell me negative 1 pumps out. The next one I would look for maybe is a 6. 6 minus 2 is 4. There's your perfect square, the square root of 4, which is 2. So negative 2 comes out. And then we'll go one more. Let's look for 11. If 11 goes in, subtract the 2, I get the negative square root of 9, which is negative 3. So there's a good set of ordered pairs that I can now use. Okay? So pause the video for a second. I want you to graph those on the graph, but before we do that, I want to show you what I'm going to do my graph based on. I'm going to put my y-axis here. I'm going to put my x-axis right here. I'm going to go by 2s and by 1s. So pause the video, graph, and then when you're set with your graph, come back on and I'll show you what the graph looks like. So you can see you didn't have to draw the f of x function, but I just drew it on this so we could see it and talk about it a little bit. But once you plotted your points here, you would have this kind of green down here look to it. So it's kind of going downwards, but notice again, this arrow does not continue on here. It's stopping right there because that's where the radicand would become now negative if we kept going. So when we compare this to the graph of the f of x function, our parent function, you can see number one, there's been a reflection over the x-axis, so it's flipping downward. That's due to this negative number out in front of the radical sign. And we've translated this initial point here 2 units to the right. And that's where you would get that from there. Sometimes we're going to see some things that look very familiar to something we've seen. This next one looks very much like our vertex form when we are doing our parabolas and our quadratics. So in this case, it is still kind of the same use where we can start at this HK. It is kind of a vertex, even though we don't see this thing curving around. It is our starting point. So if you see something in this vertex form, then I would have something that would tell me that I can start, and we'll just kind of put this to the side for now. We can start at 3, -2. So just keep that in mind. So when we go to show this, you'll kind of see where that comes in. Okay, so we want to describe the transformations that we're going to see based on the parent function. And there's a lot of things that we probably can already start to see, and that's good. But let's just kind of continue on making the table because it is also asking us to graph it. And I do think practicing this table thing, especially with the radicands, and making sure that we pick the right domain to plug in, is definitely a good thing to make sure that you just understand how to do in the order of operations and all the rest of that. Okay, so again, looking at our domain is going to be x's are greater than or equal to 3 because x minus 3 is under the radical sign. So that means my first point I would use would be 3. Now if 3 goes in, 3 minus 3 becomes 0. The square root of 0 is still 0. Then I do multiplication times -2, which is still 0. Then I subtract 2, and -2 comes out. Okay, and if you don't see that coming out, you should go stop the video and kind of just practice to see that that number comes out that way. Now the next number I'm going to use is x's are 4, because I know 4 minus 3 in the radicand would give me 1. Square root of 1 is still 1, times -2 is -2, minus 2 is -4. Then I'm thinking of my next perfect square, which is 4. So now I'm going to plug in a 7. I'm going to get the 4, take the square root, which is 2, times -2, which is -4, minus 2 is now -6. And the next one, I'm going to plug in a 12 to get 9. Square root of 9 is 3, times -2 is -6, minus 2 is -8. So that's how I would get those values. Now over here on my graph, I'm going to draw my y-axis way over here, and then I'm going to do my x-axis. I'm going to go by 2's. And I'm not going to write every single one there, but you should be able to see the idea there. I'm going to look at my one that I just did. I'll pause the video. You pause the video as well. Show what it looks like. And then maybe start writing down some of the comparisons that you see to the g function to the f of x parent function. So you can see my graph and my comments here, and we'll just talk about each one of them quickly. But when you take your table here and just plot my g of x, again, notice we're here. And obviously you want to try to draw a nice smooth curve. My kind of curve got a little crazy there. Again, I put in the parent function just so you can see. And again, notice these arrows are not curling back up. They're going to continue to go down even slightly as it gets more and more and more. So the transformations that we see, when we talk about the horizontal shift, that is coming right here. So that's telling me 3 to the right. So it was here. Now it's over here, 3 to the right. The vertical stretch, that's this number out front, the 2, meaning that it's climbing steeper, or in this case, dropping steeper. Notice how this one's steeper than this one up here. So that's doing the vertical stretch, which is because it's steeper. The vertical translation of that starting point, again, is down 2 units because of this number right out here. And again, we talked about how we knew right from the beginning this would start at 3, -2. There is 2, 3, -2. And then it flips down because of this negative out in front. So this whole thing here is reflected over the x-axis to create this down here. Now, example 5 is not really anything that we're focusing on this year. You'll see more of this when you get into Algebra 2. So I'm not even going to spend time on this one or on the graphing calculator one, because obviously without the graphing calculator it doesn't make much sense. So we're going to focus mostly on these first 4 examples. Those are really what we want to make sure that you understand the basics of these square root functions, how to set up some tables, see some different transformations of the different types of the things that we've been seeing through a lot of these functions, the exponentials, the quadratics, as well as the linears too, for that matter. So I'm going to stop it there. We're not going to worry about examples 5 or 6. And if you have any kind of questions, please feel free to ask me when I see you in class.